Schedule for today. We'll do the swapping of homework first, and make sure you only get one if you turned in a homework assignment, and also put your name on the homework assignment you're going to grade. Second, there is a new homework assignment, which is visibly short, and this will be the last homework assignment. So here it is. So take one and then pass it around. Also, you should turn in, it's extremely advantageous to you if you turn in some sort of rough draft of your project today. And that can mean a range of different things depending on your project and what sort of feedback you hope to get on your rough draft. So here are some examples of people who are turning in paper rough drafts right now. Certain other people have turned in a rough draft by, for example, sending me an email. For example, he sent me some code and he said, just run this code and you'll see. So there are two ways you could turn, or three ways really you could have a rough draft, which I'll give you feedback on. And don't worry if you completely forgot about this and have absolutely nothing, that will not directly negatively impact your grade, only indirectly. But what happens with a piece of paper is I'll read through it and then make comments on it, which you'll get back. If you send me an email today with something I can try out, or possibly a paper like this, then I'll send you a reply email with some comments on whatever you send me. The comments will help you calibrate what you need to do if you want to get a very good grade on your project. Okay. So that's 3. So remember, if you have something to turn it in right there. 4, I'm going to talk some about symbolic calculus in Sage, which is the kind of very end of the scientific computing part of this course. And then when I'm done doing that, we'll talk a little bit more about final projects, in particular how the final presentations will go during the last 2 days of class. Before I go any further, are there any questions or comments? Okay. So symbolic calculus, undoubtedly everyone here has taken a course in calculus at this point. So in calculus you learn lots of things. For example, you learn about all kinds of special functions like sine and cosine and the exponential function and so on. And that's pre-calculus. And then you learn about differentiation. And in fact, you spend a lot of time learning algorithms for differentiation. For example, the product rule, the chain rule, the quotient rule, and all these other techniques which when you combine them allow you to take any reasonably nice function and then compute its derivative. Another thing you learn a lot about in a calculus course is how to, in many cases, not as many as you like, take a function and compute an antiderivative of it in a nice closed form, if such a thing exists. So you spend a lot of time doing that, and also hopefully a lot of time understanding how to make use of symbolic integration. And so there are, of course, also algorithms in a computer for taking a function and then hopefully computing an antiderivative in terms of whatever your basic functions are. There's an algorithm called the Richter algorithm, for example. Another thing that comes up is computing limits, where you have L'Hopital's rule and so on. Computing Taylor series of functions, which really, in some cases is, or in the general case, I guess, is symbolic differentiation and limits, but in a lot of special cases, you know Taylor series already, and there are nice closed formulas for them. Solving equations and numerically approximating integrals is another big topic that comes up in a calculus course, because you learn about Riemann sums and other sorts of sums and how quickly they converge if you use some sort of approximation to the actual integral under certain assumptions. So those are kind of the standard topics of symbolic calculus. And Sage, being a mathematics software program, has functionality for symbolic calculus. And before discussing some of the kind of history and underlying code that's relevant to symbolic calculus in Sage, just to give you a sense of what's there, we'll go to the appropriate section of the reference manual. So here's the section of the reference manual in symbolic calculus, which I'll enlarge so you can see it. So it's currently chapter 4, and it has these sections on general symbolic computation, and then equations and inequalities, and then there's some extra functions, and then there's some other examples of things, and some tests and examples of using symbolic calculus. So the main section of interest is symbolic computation, section 4.1. The symbolic calculus code in Sage, I'll get into this a little bit more, but it's currently mostly built on top of a system called Maxima, which is the oldest general purpose computer algebra system. And it's something that's written in Python on top of Maxima. The interface, a lot of it doesn't really look too much like you're using Maxima. In fact, it looks, you don't know you're using Maxima at all. But behind the scenes, currently, a lot of the hard work goes on using Maxima. But the level on top of Maxima was something that an undergrad here named Bobby Moretti spent about a year doing last year as a project that was funded by Vigor, mainly, by the NSF. So he spent quite a while implementing a whole bunch of symbolic stuff on top of calculus, on top of Maxima. And then I polished it up a lot at the end and had a lot to do with the initial design. And then other people, of course, did a lot of work to fix little bugs. So there are lots and lots of examples in here. As you can see, I'm just scrolling through really quickly. Shouldn't really see this. The main thing to take away from this is it's big. There's a lot of different things here. It's actually a huge, huge thing. Like, for example, given a symbolic expression, you can turn it into a polynomial over a given base ring. That's just the random thing I've stopped on right there. Or simplify radical, given a symbolic expression, simplify radical uses certain types of rules that involve radical canonical forms, which you can read about more in the Maxima manual, to take an expression and replace it by one that's in some sense simpler. There's a whole bunch of these different simplification systems using logs, exponentials, and so on. So, and in the documentation, you can see there are examples. For example, log of x times y, simplify radical. Kind of arbitrarily, this is what it means. It turns logs of products into sums of logarithms, etc. So you can see the various sorts of things it does to functions. So there's a lot of different things like this in here. Here's another example where you have some function and you call simplify on it, and it gives you something simpler. So there's tons and tons of things. And you've probably encountered some of this one way or the other already. If you just, for example, just go to the very bottom here. If you do, for example, f equals x squared plus 1, then you'll find that f is one of these symbolic objects, which has parent the symbolic ring. So symbolic calculus, it's really, in the context of Sage, what it is it's everything that takes place in the symbolic ring, which is the ring of all symbolic expressions. So you have this thing f, and then if you do f dot tab, you'll see that there are lots and lots of functions that really kind of have a calculus feel to them. So for example, f dot Taylor for Taylor expansion, f dot integral for integrating, inverse Laplace transform, numerical approximation, etc. There's a whole bunch of different functions that have kind of a calculus feel to them, f dot derivative, etc. So that's really how symbolic calculus is kind of laid out in Sage. I'm starting with a purposely broken session, so I should probably reset that. That was part of the big finale to show you that failing. I guess I have not reset it yet. now it's really reset. Okay, so that's just to kind of give you a frame of reference. So all these sorts of things are supported in Sage, and the code that does it is a Python layer on top of the system called Maxima. And the system called Maxima, being very old has, well, it's had a long time to have its bugs fixed. So if they're not fixed now, they're probably hard to fix. So stepping back a little bit, the main software systems out there, if you're going to do a bunch of symbolic calculus, which, or if you're going to do a little bit, and you don't want to do it by hand, which often actually is a perfectly reasonable thing to do. In fact, I think before using Sage and Maxima, every time in my entire research in mathematical life I encountered any integration type problem or differentiation or anything, I literally just did it by hand, because it's really often not that hard compared to the sorts of, the sorts of integrals I would have to do in number theory. I mean, they're usually just not that hard. You can do them by hand. And of course, in undergrad calculus, you get taught a lot about computing integrals, so usually you can do them pretty well, at least. But it may be that integration in 10 years or 5 years, or maybe now, is like basic arithmetic, in that your parents are often way better at it than you are, even though you're a mathematician, which is kind of weird. But it just used to be that people did arithmetic in their heads more than they do now, for the most part. So maybe people won't do symbolic calculus as easily in a few years as they do now. And you guys will all say, kids these days don't know how to do calculus. But could happen. Anyways, there are 4 major systems out there for doing symbolic calculus, in addition to Sage. One is Mathematica, another is Maple, UPad, and Maxima. The first 3 are commercial, and the last one is free. There are 2 other systems, Axiom and XCAS, but neither, so Axiom doesn't have very many users, and XCAS isn't very mature. So, and there are a couple of other systems, but these are really the big players in symbolic manipulation. And by far the biggest are Maple and Mathematica. They have way more users than the other systems. And they're quite sophisticated, especially Mathematica. It's very fast and powerful at doing symbolic computation, symbolic integration, etc., that sort of thing. So now we're going to talk mainly about Maxima. So I'll tell you some things about Maxima, primarily because that's the one free system of the ones I just mentioned. And by the way, Maxima is pretty good, but I think if you compare the freely available software for symbolic computation today to so if you compare it with the commercial offerings, I think it's significantly worse. And if you look instead at, say, group theory, or exact linear algebra, or to some extent a lot of numerical computation too, I think that the free offerings are as good or better than anything commercially available in a lot of cases. When you look at symbolic computation, the situation just isn't like that, in my opinion. I think that some of these other systems are way ahead for various reasons. So I hope that changes. So Maxima, one funny thing about Maxima is it's spelled in 2 different ways. Initially it was spelled Maxima with a C, and it's a program that was started by a couple of people at MIT in July 1968. So that makes it pretty old. It's 40 years old, which is quite a while for a software project. A lot of people, well, some people subscribe to some sort of model of software projects kind of ramping up at the beginning, getting a lot of excitement behind them, and then they get a stable base of users, but their technology starts to show age, and so they start maybe losing out to the new systems that come along, etc. You could see this with various programs in the past, like I think UPad maybe starting to go on the decline like this, even though it was big for a long time. And Maxima being 40 years old, probably typically that kind of curve is roughly 30 years. And of course this is incredibly big, and 30 is ridiculously big, but about 15, or well, I guess about 20 years ago, Maxima was a big deal, and then Mathematica and Maple, especially Maple, came along and just completely devastated Maxima as a product in the marketplace. And that was partly because Maxima made some really bad moves, and Maple made much better moves. So for example, So I'm giving you this based on talking to people who were involved, like Michael Monaghan, one of the people who started Maple, and other people involved with Maxima. But what happened was, with Maxima, they decided that this system was, meant for running on Lisp machines and more high-end hardware, and it's mathematics, so that's what it's for, and it should cost a certain amount, and so on. With Maple, they wanted to support, PCs and as wide of a range of machines as possible, and they decided to give academic discounts. So they sold it really, really cheaply to academics and universities, and they just saturated the market. And Maxima just didn't stand a chance in that sort of environment. So, anyways, that's kind of the long-term thing. It started not really as something to make money. It started as a DARPA and Department of Energy project, and it was like that for about a decade. But then certain people convinced certain government agencies that Maxima, being very symbolic, is kind of irrelevant to defense applications. So let's put our money behind development of numerical linear algebra libraries and sort of stuff that originally was used to create MATLAB. So they lost that sort of funding, and they became a commercial company. The company was pretty good at the beginning, I guess, but then it really just fell apart, and they lost. I found last time I was in Portland, I was looking, and there are tons of books on mathematical software from the 80s in Powell's books, which is kind of surprising, in Powell's technical books that I'd never heard of. And there was one book there where they tried to compare a whole bunch of different math software systems around 1992 or something, and they really wanted to include Maxima, but they couldn't get a copy for some reason. It was just so hard to even get access to the system at that time. Maxima with a C. Fortunately, there's Maxima with the C is dead, but Maxima with an X is not dead. It's actually alive and well. So I'm not sure. So Maxima with the C was sort of dying, but in 1998, this guy William Shelter was able to get the copyright for the Maxima code. It wasn't so what happened was the code sort of branched, evidently. So there was the Maxima code that got commercialized when they lost funding, and that got developed by a company. But there was some point in which the work on Maxima was government funded, and hence the government owned the copyright. And at that point, they took that snapshot of Maxima with the C, and they made Maxima with an X. William Shelter did this, and he GPL'd it at that point in time. So instead of it being a kind of dead thing, this sort of version that goes back in time a little bit was GPL'd. There's something similar with Axiom, by the way. Axiom was a kind of a commercial project, but that got sold. But then if you go back in time a little bit, there's a version that's now has some BSD-like license. That is not the final version that was sold. It's sort of a version that was right before it got sold. So there's this history of computer algebra systems being developed for a long time, losing funding, becoming a company, doing a huge amount of development as a company, making flashy interfaces, and then that code being completely tossed. So this has happened repeatedly. Time will tell whether that sort of thing happens with Maple or Mathematica. We shall see. And also, another thing, a pattern you see here is with these computer algebra systems being government funded and then losing funding and then becoming closed and then dying. And when I talked to Michael Monaghan about SAGE, he was completely convinced that was the future SAGE had for it. That it's getting a lot of funding from various places, a lot of excitement, but then it's going to have to be commercial and closed in order to continue. It's just sort of the natural evolution of a math software system, and then it will die. But I had to kind of explain to them, but because the copyright is spread among hundreds of people, and SAGE is GPL'd, and it's derived from a lot of other GPL programs, there's no possible way it will become a closed commercial product like Maxima with the C, or Axiom before it was open source. So I think I convinced him, I don't know. So there is this system, Maxima with an X now, that's GPL'd. The person that got it GPL'd passed away 7 years ago, but just as a kind of testament to the GPL, other people just found the code, picked it up, and have been actively releasing it and maintaining it ever since. So as you can see, it's constantly being updated, bugs are being fixed, and so on. Really, as far as I can tell, there's 1 or 2 people that really genuinely work actively on the Maxima code. But there are people who do make regular releases. The mailing list is extremely popular. So there's a huge amount of discussion by users back and forth about how to use maxima to do things. And I think user-wise, I think it's easily the biggest open source computer algebra system out there as far as actual users, which means it has a few tens of thousands of users, I think, regular users. There's a lot of random people, though, who will know a little bit of maxima and will have used it. So, for example, or will have contributed code at some point in their life. It's amazing how many kind of 40 or 50-year-old people I've met who, when I mentioned maxima, they say they contributed a little piece of code to it when they were a grad student or an undergrad or something. So, and just think, in 15 years, maybe a lot of you will say the same thing about Sage. So that's maxima. So, I mean, it's a computer program, and you might wonder what sort of computer program it is. It's a Lisp program. It's approximately 100,000 lines of Lisp code. How many people here are fluent as Lisp programmers? How many people here are fluent as Python programmers? How many people are okay Lisp programmers? Like they could actually write something. How many can write something in Python? Okay. A little unfair because it's pass on Lisp. So 20 years ago, I'm sure the hands would have been a lot different because Python didn't exist and everybody learned Lisp in 50 seconds. So unfortunately, a lot of people don't know Lisp these days, and that makes it hard to work on maxima itself. Moreover, the code, if you look at it, is not that. I looked at the integration algorithm, and I think I found one comment in the whole file. So it's not commented at all. Some of it's commented a little, but it's really, I mean, you're not going to get a story about how it works in the code. So, and a lot of the comments are at the top, like written in 1980 or 1970. They're really old. It's really old code. Some of it written a long time ago. Some a little bit more recent. So there's problems with it, and it's not trivial to fix the problems. And on the other hand, a program that's been around 40 years and has a lot of users, which it does. I mean, it's crystal clear. There are a lot of people that actually use maxima because the mailing list, if you look at it, is extremely heavy volume. So it's pretty. I mean, the bugs are usually they're pretty hard to fix bugs. It doesn't have a lot of really stupid bugs in it. One recent bug I remember that came up was computing the floor or ceiling of a symbolic expression. And it turned out behind the scenes maxima was numerically truncating the symbolic expression at some point and taking the ceiling of that, and then I think maybe doing some sort of consistency check. And if you rig things a little bit, you could get it to give wrong answers, where you enter an exact symbolic expression, ask for the ceiling, which should be an integer, and you get something that's just wrong. And a much preferable thing for it to do would be to give you either the right answer or an error message if, for example, it's just impossibly hard to compute the ceiling. You can write down expressions where it might be very, very, very hard to compute the ceiling of a number. I mean, think about it. If you had some complicated symbolic expression involving e and pi and all kinds of other things, you might not know how many digits you need to go to in order to provably evaluate that expression to some number of digits of precision. So we complained about this being broken in maxima and hence in Sage on their mailing list. And they said, yep, it doesn't work. And then they started trying to figure out how to fix it and came up with some crazy ideas that are clearly wrong, involving just computing with more digits of precision, but with no real understanding of what you're doing. And then somebody else said, hey, that's never going to work, and we need to implement blah if we're going to be able to correctly fix this bug. By the way, what do you think blah is? Thinking about things we've done so far.
Basically around.
Well, I'm imagining symbolic expression. So you have this expression involving pi and e and square roots.
Intervals?
Interval arithmetic. Yep, you need interval. If you have interval arithmetic, you just compute and you replace all the symbolic constants and everything in your expression by intervals. You multiply it all out, and if the interval is from minus 3.1 to minus 3.4, then you can easily compute the ceiling and floor of that number. On the other hand, if it's from minus 3.1 to 2.4, you don't know, because there could be anything in there. So you don't know what the ceiling is. So you just increase your precision, multiply everything out using intervals, and you the answer. So they concluded that on the list, but then they realized they didn't have an interval arithmetic package, and so they just gave up. And so it's still not fixed, which is kind of annoying. But I mean, if you think about it, if somebody wanted to have interval arithmetic in maxima, they're going to have to just sit down in Lisp probably and write this whole interval arithmetic package. And there's basically one guy working on it, and his hand's very busy doing releases and just keeping the project going. So unfortunately, it just doesn't move forward so well. So personally, we just changed our implementation to use our own interval arithmetic package. So the floor and ceiling and Sage work fine. So when you do, like if you make some, I think we have actually some of these funny examples in the doc tests. Yeah, here's the one that's wrong in maxima, I think. So when you do this, it uses interval arithmetic. So factorial 50 over x of 1. I don't know if that's actually the one that's wrong in maxima. It might be. Find out soon enough. What? Oh, it might not actually be called floor there or something. Actually, a problem is that factorial in maxima isn't. I don't know the floor command in maxima, so it's hard for me to. What is floor? Oh, it looks like they've updated their, maybe they've, look at this. So here you can actually see them explicitly saying that it doesn't really work in a sense. They say they use floating point evaluation. It's possible, though unlikely, that floor could return an erroneous value. To guard against this, a floating point evaluation is done using 3 values. So, I don't know. As a mathematician who wants right answers out of my software, that makes me very nervous. Doesn't say what 3 values and why are they doing that in the first place. So this is just to give you a sense that the way Sage builds its symbolic computation, which is you have maxima here, and then you have this Python library on top of it, which Bobby Moretti wrote, has its issues because if there's something really screwy about how maxima works, then that can be inherited by Sage. And it can be a lot of work. In the case of floor and ceiling, it's easy. We just write our own version that uses intervals. But in some cases, it can be really hard to get around the weird things that maxima does. For example, what if in some sort of integration algorithm, maxima internally, I don't know why it would, but uses its built-in floor? I'm not sure why this isn't giving any answer, by the way. But if it used its built-in floor, then it'd be giving wrong answers in some cases, which would be disturbing. Sorry, I'm really annoyed by this. Floor. Okay, I guess it just doesn't. Try to flow to that. Nope. I guess it just says, no, I'm not going to do it at all. I refuse. Maybe that was their fix. They just decided that if they're somehow worried about their answer, they just give you back the question. It's kind of a typical thing symbolic algebra systems do. Instead of saying, no, I can't do it, they just ask you the question back, like some Zen monk or something. So that's maxima. And now the rest of the lecture is to give you a sense of what the options are if you need to do some integrals and symbolic stuff, like compute limits, etc. in Sage. What options do you have? So there are 3 right now. And at the very end, I'm going to tell you what's on the horizon. So the 3 options in Sage right now, Sage includes maxima. Every single copy of Sage has maxima in it. And so you're trying to do some symbolic calculation. You're not going to use Mathematic or Maple. You don't trust them at all, or you just don't have them. You look around the Sage reference manual and you can't find anything that seems to do what you want. Like you have maybe you have an infinite series and you want to find a closed form expression for it. And nobody's got around to implementing anything to even make it look like you can do that in Sage. But you Google and you find that maxima can easily do that sort of calculation. So one option is you can simply just copy and paste the code from the reference manual for maxima right into Sage in a box that you label with %maxima. and you'll get what maxima does if you give it that input. So I've completely messed everything up. Okay, so given this input, integrate sine of x times cosine of x with log of 3x, which that's not the world's hardest integral. You'd expect a calculus student to be able to do that. I don't know if I could do it, but you'd expect that you can do it. And there it is. Maxima's done the integral, and it's got the answer that was there. So, and there's a lot of other things that I'll show you in a minute. You can also do exactly the same calculation by typing maxima.eval, and then giving as a string, oops, the input, and then you'll get the output as a string. So you could then try to parse the string in some way or something. So in some cases, I've certainly used that, because there's a lot of examples out there involving maxima, maxima code, etc. So you can do this. And the maxima language itself, when you work with maxima, you don't work it with the language that it's written in. You don't work with Lisp. It's written. They have their own language, which of course goes with every computer algebra system having had their own math language. And maxima has its own as well. So for example, to assign a variable a value in maxima, you do, if you want to set a equal to 2/3, you do that, a colon 2/3. And now, after doing that, a is, oops, I forgot the quote. A is equal to, wrong quote. A is equal to 2/3. So it's not like in Lisp where you use parentheses set q a 2/3. It's its own thing where you use a colon. Which I don't know any other language that does that, but that's what maxima does. So it has its own entire language you have to learn. But there it is. So that's one of the three options. So we have one maxima directly, so raw. And you have the Sage calculus code, which you've already used a lot probably. And this is the thing again that Bobby and I wrote on top of maxima. And then you have, the order is different from what I have here. Then you have SymPy, which I'll also talk about. SymPy is something that's completely distinct from Maxima. It's a pure Python library that was started about 2.5 years ago by a Czech guy named Andrej Štěrtek. And it's nice because it essentially has no dependencies. It's a pure Python package. You just download it from its website. You install it into any Python running anywhere, and it just works. And it does a lot of symbolic calculus. And I'll show you that in a minute as well. So let me just show you a few examples. Illustrating doing a couple of standard operations involving symbolic integration, differentiation, limits, sums in Maxima, in Sage, and in SymPy. Okay? And then after that, I'll give you some sense of where symbolic calculation in Sage is going. And yeah. So here's an example of differentiating a function. It's just the integral that we got before, so we're double checking it. Here's an example of timing, creating that expression and differentiating it in Maxima. So this isn't really timing how long Maxima takes to do it. It's timing how long it takes for Sage to say, please, Maxima, compute that derivative of that expression and give me the answer back as a string. It ends up taking 5.9 milliseconds to do that one thing. So it gives you a sense of the amount of overhead there is in each call to Maxima and getting the answer back. I already showed you that. So you can integrate as a string, calling the integration. The time is basically the same because the time is mostly just overhead and calling back and forth to Maxima. In fact, just to give you a sense of the overhead time, let's ask Maxima how long it takes to compute 2 plus 2. Again, yeah, so you can see that over half the time here is in overhead. On the other hand, these times aren't that bad if you think about it. It's completely different. Sage is talking to a completely different program, so it's pretty fast given that that's what's going on. Here's another example of defining two functions using colon. F is sine x cos x plus log, and g is the integral that we computed above. multiplying them together and expanding out the result. So again, Maxima does that, and it takes about 6.8 seconds. So Maxima are milliseconds, and Maxima is taking about 3 milliseconds, and the other part of the time is just overhead. Here's an example of a limit where Maxima is really annoying. Maxima has this incredibly obnoxious habit of asking you questions interactively about the status of your variables, where I think what Maple would typically do in this sort of situation is it would say, the answer might be different if x plus 1 is positive or negative. I'll compute both possibilities. If they're the same, I'll just give you the answer. If they're different, I'll give you, some sort of little brackets notation. It's kind of like the intelligent way you would answer a question on an exam, by giving the full answer, answering all possible questions the instructor might ask you. Maxima, on the other hand, interactively asks you questions. So we actually spent a long time at the beginning trying to get it so that you could work with Maxima, and when it interactively asks questions, it wouldn't really be interactive. So you have to watch for it to ask a question, and then just always tell it no, and then bring back the prompt to the user. So it's actually something that a lot of people have tried to use Maxima as a backend for symbolic computation engines and web pages and so on. And the fact it has this interactivity comes up constantly and bugs people like crazy. So in any case, you can, in this case, you can say, well, I'd like the limit from above, and then it doesn't ask you the question. You can also explicitly say, assume x plus 1 is greater than 0, and then it will be able to do the calculation. So if I explicitly put assume x plus 1 greater than 0, actually I'll assume it's less than 0, then it gives the answer. This is literally the string output Maxima gave for doing that and then doing the next one. So that's why it looks complicated. Right, it does give the answer. Okay, let's see. Now here's something that no one's ever wrapped in Sage yet for some reason. We just ran out of steam. But you can type in an expression for an infinite sum. For example, sum of 1 over 3 to the n plus 1 over n to the 4th, this infinite sum. As n goes from 1 to infinity. And in many cases, just like you could if you were in a calculus course, Maxima can figure out what this expression is supposed to be. It'll find when possible, it'll find a closed form expression for it. So here what it does is it says, hey, this is a geometric series, so you get the half there, and oh, this is the, remember there was that formula of Bernoulli, or actually, the formula of Euler for the sum of 1 over n to the k. And it's some power of pi over some Bernoulli number. So that's what it does, and it gives you this closed form answer. Sage should be able to, you should be able to type in expressions like this directly into Sage without having to know about Maxima and get the evaluation of this. But nobody's implemented that in Sage yet. So one reason to use Maxima might be just, if you're too lazy to implement that, you could use it for this purpose. But it is kind of nice to be able to, to be able to do this.
William, things like that are just stored in a lookup table, or what's going on? How does it know that that's pi to the 4th over 9?
How does it know?
Yeah.
Well,
you've given us an
I don't know. Read the Lisp.
So,
read the Lisp code. I don't know. I mean, you can look at the documentation for the sum command. I don't know the algorithms that are implemented. But I assume that at a minimum it probably breaks it up into the summons, or possibly combinations of summons.
So and then it gets a decimal.
I mean, everything's a lookup in a computer. It doesn't compute a decimal approximation. I'm sure it doesn't do that.
Okay, so it must.
It doesn't compute a decimal approximation and then find a number that looks like it's equal to it. It actually must have encoded in the algorithm this formula of Euler. Yeah. So Robert, you wanted to make a speculation?
I was just going to say, once it breaks it up, it wouldn't be hard to have a formula. Oh, I know how to handle one.
Yeah. It just looks at it.
Well, but it can I imagine it has a lot of code that can transform things to fit what's in the data.
Okay. There are going to be many things that we'll talk about.
Yeah.
There's a lot of useful things though. I mean, because there's a bunch of things like this that you encounter in a calculus class. It can be automated. And people, I mean, undoubtedly there are research papers about given us an expression in some form, how do you get a computer to do the problem that you get calculus students to do every day. So, Okay, so that's maxima. And the one other thing, maxima is, despite the size in lines, it's pretty big. If you look at there's a reference manual which is pretty good, and there's a lot of different things in there. It's pretty amazing, size-wise. But it's really, I mean, it's 40 years old, and I don't know what future it really has. And just, I mean, Lisp is great from a theoretical point of view, but the Lisp ecosystem these days is not so good. It's pretty hard to get a good Lisp compiler, and my experience hasn't been so great with maintaining Lisp code. And in particular, finding people to work on Lisp code isn't so easy. That's a big problem. So there you are. Okay, SymPy, it's this pure Python library for symbolics. And I guess the main thing to keep in mind about SymPy is it's pretty new code, and it's all in Python. This means it's potentially slow. A lot of people have criticized it for being really slow, and as a consequence, a lot of other very clever people have made it faster. For example, last summer there were 5 Google Summer of Code projects somehow all about improving SymPy. So there's been a lot of effort that's gone into improving SymPy by various random people. And then some of the people in the Google Summer of Code projects last year forked SymPy into SymPy Core, which was an attempt to make it even faster via various methods. So it's an interesting project. And anyways, let me just show you some of using it. But there are a lot of people that like it, and it's really valuable that it's really lightweight. You know, you can look at the code. It's being very actively developed today, and the first thing I tried when I was making this demo yielded a bug, which was I asked for the integral with respect to x, and it gives me a name error, global name, equality is not defined. And if you look at the corresponding Python code, it uses the word equality right there in the code, but equality isn't defined anywhere in that scope. So it's just wrong. So I filed a bug report. But if you integrate without the symbol there, you don't get an error. You just get the send answer back, which is the original question. So I guess it doesn't do really hard integrals like cosec sine x plus log of 3x. Let's see. But it does do derivatives, and it's supposed to be pretty good at limits, and it's fast. I mean, so this is timing differentiating that. I'm a little worried that I might be caching it, so I'm going to retime creating the whole thing and differentiating it. That time is so fast, I bet it's caching the answer. Whoa, what happened? Oh, I just made my font smaller. That's a little unfair because it's creating the whole expression. So ignore it. To some extent, you should ignore the timing I'm doing here because it was so fast just a minute ago when I just had g.diff that I suspect that it did the differentiation once and then it remembered the result by storing it in an attribute of the Python class. And you'd have to look at the source code to see if it's doing that or not, and then you'd have to turn that off somehow in order to properly benchmark this. So I may be just being misled by the benchmark. On the other hand, creating the whole expression takes a long time, so it's really unfair. Actually, a good thing to do in this case is, so that's actually a good benchmark. So I took G, I added 1 to it, so it's creating a new object each time. There's no way it's caching that. Python wouldn't let you do that. So this is actually probably a reasonable timing. And 9 microseconds looks pretty good. So it's pretty fast now at certain operations like differentiation. And also arithmetic, it's pretty good. So here, I compute the product of 2 symbolic expressions and expand it out. It's not too complicated, that's the expanded form, but the time is 520 microseconds. Doing exactly the same thing with Sage, we'll see in a second, is slower. And I'll compare the times in a second. So you have SymPy, and now here's Sage. This code, which you've surely already used a lot already, this is just what you get by default when you start up Sage and start messing around with x and sine and cosines. It's actually the first thing a lot of people see when they use Sage. So it gets your homework done, and who cares if it's 30 milliseconds versus 30 microseconds if you're computing one integral for some other reason. So here, it also has a nice time saving feature. So here's an example where I've entered exactly the same functions f and g as I did with SymPy and expanded out, well actually computed the product and then expanded out. So I just get some big mess. And now I'm going to time it, and you can see what the ratio of timings is. So this is just what you would naively get if you were using Sage. It's like 39 point, I mean the timing varies, but it was 520 microseconds versus this time 39.5 milliseconds. So a factor of 76. So that's pretty significant. And that's a serious problem. If Sage in the interpreter is 100 times slower than a symbolic calculus package written in pure Python being used from the interpreter, something is clearly very wrong and needs to be fixed. The reason things are like this is because a year ago our option was to, first SymPy was so new and so kind of messed up a year ago that it was massively buggy, so we didn't just build things on top of SymPy. And also SymPy just it does some arithmetic, it has a couple of functions in it, and as you can see, it doesn't do even basic integrals. So there's a lot of issues with that. So what's the future? So as you can see, Sage is symbolic calculus, though very full-featured. I mean, it's very powerful because Maxima does have a lot of stuff that's been written over the last 40 years. And most of it is pretty well debugged in Maxima. The floor ceiling thing was an example where you run into funny situations. It's slow. And not only is it two problems. One is that it's slow, which isn't the end of the world. For a lot of applications, being 100 times slower for computing a symbolic integral doesn't really matter very much. Imagine doing your homework problems. However, or making homework problems as a teacher. However, there's another major problem, which is that Maxima is written in Lisp and not documented very well. And this has the impact that it's really hard if people want to modify and greatly improve Maxima for their own purposes. So for example, Josh Cantor, who you know from his multi-dimensional numerical optimization stuff last week, really wanted to write a differential geometry package building on top of Maxima last year. And he dived in and tried, and it was just way too hard to get his head around the system at all, because it's pretty archaic and not well documented and so on. So it's really hard to get into working on Maxima, as evidenced by just logic of the system not being well documented and so on, and also just the fact that there aren't that many people working on it. That's an indicator. However, there's other issues with Maxima. Here's a good one. This came up the other day. I was giving a talk at Seattle University and I tried to get this integral, and I got this weird error, too many contexts. This comes from Maxima, just some random integral I gave it, and now Maxima is completely broken for the rest of the session. You have to restart the copy of Maxima. You can try it right from the command line in Maxima, try to compute the same integral, and it just goes boom, and it's broken henceforth, which is really weird. So there are lots of these little problems. Here's what our future plan is. So this guy, for the last 6 months or so, Gary Furnish, has been working on completely rewriting entirely in Python all of the symbolic calculus stuff in Sage. And he's going to spend his whole summer full-time working on this, partly as part of Jim Morrow's REU. And that is really, I think, our best hope for having much more sophisticated symbolic manipulation functionality, which will be really, really fast, faster than anything you could do in pure Python. And it will also fit much better into the kind of general framework of Sage, where you'll be able to say that you're doing symbolic calculus, but your x is an integer. And you'll say that in a more precise way than you can currently do it. That's really the future. And there's going to be a huge amount of work that's needed to carry this out, like implementing integration and so on. Okay, so I'm done. I didn't get to talking about the final presentation, but I will do that first thing on Friday. Okay? And if you have any